All right, let's talk about predictive modeling. It's this amazing, sometimes kind of tricky world where we try to build models that are genuinely smart. But the real challenge, it's finding that perfect Goldilocks zone. Not too simple, not too complex, but just right. So that brings us to a huge puzzle that's really at the heart of all of this. Why is it that these incredibly powerful, seemingly brilliant models can sometimes fail in the most spectacular ways? That's the big question we're going to unpack today.
Okay, first up, what is the prediction problem, really? Well, at its core, you can think of it like we're teaching a computer to see the future. We feed it a bunch of data from the past, it chews on that data and learns the patterns, and then we ask it to make smart guesses about new stuff it's never, ever seen before. Sounds simple enough, right? Heh, well, not quite.
The real trick is in how we measure what good even means. You see, there are two different kinds of error. First, you've got in-sample loss. That's just how well the model fits the data it's already seen, the training data. But then there's generalization error, and that's the one we really care about. That's how well it performs out in the wild, on new data. And here's the kicker. Getting an A+ on the practice test doesn't mean you're going to ace the final exam. And that leads us straight to the main villain of our story, the overfitting trap. It is so seductive, but it's incredibly dangerous. It's what happens when a model gets so obsessed with the training data that it starts memorizing every little random quirk and bit of noise, instead of learning the actual underlying signal.
Let's make this real. Take a look at this. We've got 20 data points and we're trying to fit a line to them. But we could draw all sorts of lines, right? A simple, straight one, or a slightly curvy one, all the way up to these incredibly complex, squiggly ones. A lot of them look like they kind of fit the data. So the question is, which one is actually the best?
Well, if we only look at how well they fit the data they've already seen, that in-sample error, we get this graph. And wow, as the models get more and more complex, their error just goes down, down, down. That ninth degree polynomial, the most complex one we've got, it looks like an absolute genius. It's got almost zero error. So we should obviously pick that one, right? And snap. There's the trap. The moment we introduce new data points, those blue triangles, our so-called genius models are a complete and utter disaster. Just look at that crazy complex curve. The same one that hugged the original data perfectly now misses the new points by a mile. It wasn't learning the pattern, it was just memorizing the noise. This is overfitting, right here in front of us. So, to put a formal name on it, overfitting is when a model learns the training data too well, noise and all, and then can't handle new stuff. And, the opposite problem exists too. That's underfitting, where a model is just too simple to even capture the basic pattern. Our whole job is to find that perfect, just right balance right in the middle. So how do we actually fight back against this overfitting monster? Well, our first strategy is a little counterintuitive. Instead of trying to build an even more complicated model, what if we just gave our model smarter data to begin with? This is the first part of our toolkit. This is a process called feature engineering. It's basically the art of using your own human knowledge about a subject to create new, more powerful inputs for the model. Think about it like this. A doctor doesn't just look at height and weight separately, they calculate BMI. They're creating a new, more meaningful feature. By doing that, you're giving the model a massive head start.
But here's an interesting question. Do all models need the same amount of help? This table shows how 4 different types of models did when trying to learn 16 different kinds of patterns on their own. Now, the key here is that a lower score is better. It means the model was good at figuring things out by itself. So, what's this table telling us?
The biggest lesson here is that one size definitely does not fit all. Neural networks, for example, are super flexible. They can figure out a lot of this stuff on their own. But look at that last point. Every single model, even the fancy neural network, completely failed to learn a feature called ratio of differences. So what does that mean in the real world? Well, imagine you're predicting apartment rents. That feature could be something like the difference in rent per square foot between the master bedroom and a smaller bedroom. It's a really subtle, nuanced idea that none of the models could figure out alone. That's where the human analyst becomes the absolute MVP. Okay, our second big strategy comes at the problem from the complete opposite direction. Instead of just making the input smarter, we can actually put the brakes on the model itself to stop it from getting too complicated in the first place. And this amazing technique is called regularization. The idea is actually pretty simple, but it's so powerful. We basically add a complexity penalty into the mix. We're telling the model, look, I want you to fit the data well, I really do, but I'm going to penalize you every time you make yourself more complex. This forces the model to only focus on the patterns that are really important. Now let's look at the two most common types of this. And hey, don't worry about all the math here, just focus on the tiny difference at the very end of each equation. On the left, we have lasso, which uses the absolute value. On the right is ridge, which uses the squared value. It seems like a tiny change, but that little difference leads to a huge difference in how these models behave. And you can see that behavior right here. Each of these colored lines represents how important a feature is. As we make that complexity penalty stronger, moving from left to right on the chart, both methods shrink the importance of the features down towards zero. But check out the lasso plot in the top left. Do you see how it forces a bunch of those lines to go all the way down and hit exactly zero? This is incredible. It's doing automatic feature selection. It's literally telling us which inputs matter and which ones we can just throw away. So we've got these two really powerful tools in our toolkit: crafting smarter inputs and taming the model's complexity. And it all comes together in this one final, really elegant idea: the art of balance. In the field, this is what's known as the bias-variance trade-off. Bias is basically the error you get from a model that's too simple. That's our underfitting problem. Variance is the error from a model that's way too complex and jumpy. That's our overfitting problem. And here's the thing, you can't get rid of both at the same time. If you decrease bias, you're going to increase variance, and vice versa. The goal of a great data scientist is to find that perfect sweet spot, that ideal trade-off for whatever problem you're trying to solve. And that leaves us with one last really crucial idea to think about. In the world of predictive modeling, the number one goal is just that, prediction. While understanding why a model works is great, it's not as important as how well it works. The model doesn't have to perfectly explain how the world works. It just has to be really, really good at predicting what's going to happen next. And mastering that trade-off, well, that's the true art of finding the just right fit.